Thank you.
Let me see, I put together a few slides if you can give me
Yep.
the ability to share screen.
Yep.
Mostly just pictures, but yeah.
That's great.
All right, you should be good.
Okay. Let's see, and of course, my thing is blocking. There we go. Oops. All right, we'll get this worked out eventually. All right, there. Why does it say I'm paused?
We can see it from here, but if you try
Okay.
to like, skip a slide or something, we can let you know if we don't.
Yeah.
See change.
Can you see the slides moving?
I cannot.
You cannot.
Correct.
I don't even know how I did that. Oh, here we go. Now can you see?
Yes.
All right. I didn't even know you could do that in Zoom. But anyway, thank you for inviting me to speak this evening. I'm happy to see that there's a good number of attendance for your AIAA meetings. So that's a good thing to see that there's strong support for an AIAA student branch at NC State. That's certainly something I'm an advocate for, and been an AIAA member myself since I was a student, and now I'm senior level membership. So it's good to see. Today, obviously, I made these slides as Froberg Aerospace instead of NC State. That gives me a little bit more freedom to talk about stuff that I'm doing outside of NC State. So please consider all of the information and opinions I'm providing to be in my role as CEO of Froberg Aerospace and not as a member of NC State faculty. Though there's not any real, I'm not going to get into any legal trouble representing here or anything, but anyway. So today I'm just going to talk about some of my background and what I've done before, I came to NC State, and then sort of talk about just sort of a high level overview of my research programs. And my research programs are all done through my small business, Froberg Aerospace, currently. So I'm going to give you an overview of what we're up to and some of the things we've done in recent years, and sort of where we're heading next. But anyway, as Christian mentioned in his very kind introduction, thank you for that again. I went to Missouri University of Science and Technology for my college education. If you're unfamiliar with it, this is a reasonably small school in a small town in Rolla, Missouri, but it is basically the engineering school for the state of Missouri. Now, there is a program at the main University of Missouri campus in Columbia, but frankly, in my opinion, it's lower quality than Missouri S&T. Let's just put it that way. So I got my bachelor's in aerospace in 2010 from that school. At the time, I was looking for a job, but there weren't really many available because during the 2010 timeframe was the height of the economic recession. And so, the only jobs available were, jobs that I didn't necessarily want to pursue. Certainly not a lot going on. Not a lot of hiring going on in the space realm of things, certainly not in rocket propulsion that I could find anyway. And it was very competitive at the time. So like a lot of my fellow classmates, or a large number of them, I chose to go to graduate school. And by the time I made that decision, most schools' application deadlines were already passed. So S&T had a very generous application deadline. You didn't have to apply until I think June or something like that. So I ended up applying, stayed to get my master's degree. that worked out, I think, pretty well. I found a project that I really liked doing, which is very important in graduate school, which I'm going to talk about today. I'm still doing it, in fact. And yeah, liked it so much. I stayed and got a PhD. That was completed in 2015. I want to note, and I always tell people this, that there's a lot of pressure on you as students to get internships, as early as freshman or sophomore year, which is a little silly in my opinion. But I didn't have any internships throughout my undergraduate career. I think I turned out okay. In fact, I didn't have any summer work until 2012 when I got a position at AFRL Kirtland Air Force Research Lab in the Space Chem 2 lab, doing some spectroscopy experiments on ionic liquids. And I'll talk about those in this presentation. But spectroscopy is essentially shooting laser beams at these chemicals. We brought them into gas phase and shot laser beams at them to discern information on their structure and how they behave, so we can eventually improve models of these things. Some of the activities I did when I was an undergraduate, I was involved somewhat in AIAA, but more so in Sigma Gamma Tau. And I was also chief engineer senior year of our rocket design team, which participated in the NASA University Student Launch Initiative. I don't know what it's called now. It might just be Student Launch Initiative. I haven't kept up with it, but that's a picture of our entrant that year. I'm on the bottom right there. And it was what's known as a kangaroo configuration. So it was a two-stage rocket where the second stage fins were hidden underneath I guess you could call it a payload fairing or a shroud to reduce the drag of that. And then for stage separation, it activated a piston, activated via black powder, and pushed the second stage out of the shroud there and ignited it at the same time. So we were able to get it to separate and ignite successfully. We could never get the second stage recovery to work out as well as we planned. So anyway, so I guess sort of during my PhD program, started working summers at SpaceX as a propulsion systems development engineer, first as an intern and then full-time. Really before I started or ended my PhD, I started working full-time with SpaceX. And again, I was a propulsion systems development engineer. So propulsion systems is all of the fluid components that is not in the engine. Okay, so at the time, there was a propulsion systems team and a boost team, and boost was responsible for the engine, propulsion systems responsible for everything else that involved fluids, whether it be the propellant tanks themselves, the pressurant system, ACS systems, etc., that were on the rocket. So some of the projects or main projects I worked on, SpaceX, if you work there, it's something different every day, but nonetheless, there was some overarching major projects I worked on. One was a propellant utilization system for the second stage. And that is important because, figuring out how much propellant you have left on board, or really the difference between what you have in the fuel and oxidizer tank, is important to know so the engine can adjust the oxidizer fuel ratio so you don't run out of, say, oxygen way before you run out of fuel. Okay, so you don't want a lot of propellant left over, because that's bad, because you didn't use that mass, and that's essentially dead mass now. So that's one of the things I worked on. Grid fin hydraulic system, if you've ever seen the first stage, well, I guess sort of return to Earth after it's dropped off the second stage. It deploys grid fins, and those are controlled via a hydraulic system that has actually evolved several times. But I worked on some of the early versions of that. We blew up a rocket in was that mid 2015. And that was associated with a part of the pressurant system in the second stage. So I was part of that failure investigation. We set up a test to try to replicate some of what happened on that failure, and did that out at Berg Air Force Base. It was kind of cool actually to do, because it's sort of it's different than normal, I guess, design and engineering work. It's more like detective work, which is interesting. Let's see. Yes, properties of subcooled RP1. So one of the things SpaceX wanted to do in order to be able to land the first stage rocket, they had to pack more propellant into the same volume of the Falcon 9, so they would have enough propellant left over to use for landing. Okay, so one of the solutions to that, which they ultimately pursued, was to subcool the propellants, which makes them more dense, and thereby you can store more propellant mass in the same volume. Okay, so I worked on, there were certain phenomena that I can't really talk about that happens with RP1 if you cool it below, room temperature, in terms of the chemistry, and so I worked on that a little bit. Another thing I worked on was stage separation mechanisms, specifically how to keep the TVC on the second stage from, I guess, moving during stage separation. We did something interesting there, but not sure I can talk about. So I informed SpaceX about 3 months before I ultimately left that I was going to be leaving. So I walked in that day and didn't know whether they were going to fire me immediately, or asked, do you want me to stick around for 3 months? And they did want me to stick around for 3 months. But then probably a week later, they had a test engineer basically walk out of, off-site in the middle of the night and left the company. And this was right during the Flight 21 campaign, which was the return to flight after the CRS-7 failure investigation. Also happened to be the first flight using the subcooled propellants that I mentioned before. So it was sort of all eyes in the company were on the Texas test site right then, because they were testing the first, second stage engines for that flight. So I was sort of voluntold to transfer to Texas for the final 3 months and be a test engineer on that program, which was really fun for 3 months. We learned a lot about, I would say, subcooled propellant fluids, LOX and RP1 especially, and there were definitely some hiccups during that campaign. But ultimately, we got it launched, and that resulted in the first stage landing. So that was pretty exciting. I can confirm the bill at the bar that night was rather large. Yeah, somebody posted the receipt on the internal SpaceX sharing campaign, which was just outrageous. But anyway, yeah, that's my time at SpaceX. So why did I leave? There wasn't anything I didn't like about working at SpaceX, really. I left because I got an opportunity to sort of start my own company. So when I was working at SpaceX, my research advisor called me and said, "Hey, I've got some money to do a postdoc. Would you want to come do that? Because I know that eventually, or at least you told me, that you want to eventually start your own company. And so we could do that and spin off the multi-mode propulsion technology into a company." So I took that opportunity, and we co-founded the company Froberg Aerospace in 2016, which again is focused on development of multi-mode small satellite propulsion systems, and I'll get to what those are in a few slides. We got our first revenue in 2017, our initial NASA SBIR Phase 1 contract. So SBIR, if you're not familiar with it, is Small Business Innovation Research. It is research dollars, or it's supposed to be research dollars, that are allocated from government agencies. So it's NASA, DoD, NSF. If you're not aerospace, NIH, National Institute of Health has SBIR. There's a bunch of them. But they allocate funds for small businesses to do projects that are eventually geared toward eventual commercialization of technologies. Okay, so we get our first contract in 2017. That moved to a phase 2 project in 2018. That specific project just ended in early January of this year. Okay, over the course of the past 3 years, we've done other projects in addition to the NASA projects. Worked with the National Reconnaissance Office, Air Force. We've got a current project with DARPA, the Defense Advanced Research Project Agency. Okay, and it should be noted, our revenue to date is all research and development contracts. Our technology is still, I would say, very much under development, though we've made quite significant progress, as I'll highlight, in the last 3 years. But we're not selling propulsion technology yet. Okay, we've still got a little bit of ways to go before we get to that stage. All right, so I'm going to move on and talk about our technology. So a little bit of background. I see a few of you from my rocket propulsion class and some of you from my space environment class, but hopefully the rocket propulsion people already know this. I hope. I haven't graded your test yet, but we'll see. So our technology is an in-space propulsion technology, which means it is propulsion technology to provide maneuverability to spacecraft, specifically when they're already outside of Earth's atmosphere. Okay, so this includes several different maneuvers, including orbit changes, station keeping, reaction control, RCS, and/or pointing maneuvers. This is almost exclusively done, except for slew maneuvers like pointing maneuvers, by rocket engines. Okay, there's really no other way to do translational changes in space. The only game in town is rocket engines, which are governed by the rocket equation. And that states that the change in velocity is equal to the specific impulse of the rocket engine, which is a metric defining its performance, times constant G naught, times the natural log of M0 over MF. The difference between MF and M0 is the propellant you burned to do the maneuver. Okay, so specific impulse and thrust are 2 parameters you need to know if you're not already familiar with them in terms of our discussion today. So specific impulse is essentially more or less equivalent to the gas mileage or the miles per gallon of the rocket engine. Okay, it states that how much bang are you getting for your buck in terms of how much fuel you're putting into each. So how much total impulse is 1 kilogram of fuel imparting on the spacecraft as utilized by your rocket engine. Okay, and then thrust is simply how much force can the engine output, okay, for a given propellant flow rate. Okay, there's essentially 2 types of rocket propulsion. One's chemical and one is electric, that we'll talk about now. So chemical propulsion is what most people associate with rocket engines. That's where thrust is produced via chemical reactions. Okay, picture of the Saturn V there. The gas coming out of the engine, hot gas is produced by a chemical reaction of rocket propellant 1, which is a refined kerosene, and liquid oxygen. So chemical propulsion is really good for producing large amounts of thrust. It is the sole, really the only game in town for launch vehicles. But the downside is its specific impulse is relatively low compared to other types of propulsion. Okay, so it can produce a lot of thrust, but your gas mileage is going to be a lot lower. compared to electric propulsion. Okay. Instead of producing thrust via chemical reactions in electric propulsion, you produce thrust via propellant acceleration through electric and sometimes magnetic fields. Okay. And there's really three types of electric propulsion. One's electrothermal, which is arc jets, if you heard of that, or resistojets. Others electrostatic, which are ion thrusters and electrospray thrusters, which I'm going to talk about today. And then you have electromagnetic varieties. The most popular, let's say, electric propulsion system by far is the Hall thruster system. And PPTs are reasonably popular for small satellites. Okay. But the bottom line is they have much better specific impulses. So they use the propellant fuel a lot more efficiently than chemical engines. So they can produce larger delta Vs, but the downside is the thrust is a lot lower than chemical propulsion. So it takes you a long time to actually do that delta V maneuver. So if you want to get somewhere very fast, you can use chemical propulsion. The downside is you can't go very far. Electric propulsion is exactly the opposite. You can go really far, but it's going to take you a really long time. So that brings me to multi-mode propulsion, which is what my research area is and what technology my company is focused on. And that is the integration of two or more propulsive modes into a single spacecraft. Okay, just by definition of multi-mode propulsion. The key differentiator for multi-mode propulsion as opposed to what we call hybrid propulsion is that multi-mode propulsion specifically shares a propellant, meaning that the propellant can be used either in chemical or electric propulsion. Okay, so there's a breakdown I've shown on this slide here. So hybrid propulsion, and hybrid gets thrown around a lot in rocketry, and we wanted to make this distinction. We defined a multi-mode propulsion. And that hybrid propulsion is just, okay, you have a chemical engine and it has its propellant, and you have an electric propulsion system and it has its own propellant. Okay, and you could strap those both on a single spacecraft, and people have done that before, but they don't make use of shared propellant. So you can't choose how much propellant you're going to allocate between electric and chemical propulsion. You have to choose how much you want to allocate before the satellite is launched. Multi-mode systems make use of shared propellant, so you can have different types of those. So it breaks down further. One that's been used before is an all-chemical type system. So a typical bipropellant in space combination is nitrogen tetroxide and hydrazine. And those are hypergolic bipropellants, so they can be used in bipropellant engines. But hydrazine is also a pretty good monopropellant. So there's been systems that have utilized hydrazine and burned it with NTO in a bipropellant engine, but also use some of that hydrazine for monopropellant, usually for ACS type maneuvers. And so, let me see, this is what we consider a partial multi-mode system. Because notice you can only use the NTO for the bipropellant mode. You can't use it for monopropellant. So there are all electric multi-mode systems. So one example is the dual mode Hall thruster, which most Hall thrusters are dual mode now and can run in a high ISP mode or a high thrust to power mode. So they sacrifice a little bit of ISP to get a little bit of higher thrust. And that's, would be considered multi-mode by our definition. You can also do this with ionic liquid electrospray, basically the same thing. But really where you're going to see advantages for multi-mode propulsion is when you can combine chemical and electric propulsion on the same spacecraft, okay, and make use of a shared propellant. Okay, so a classic example, and this was, I think, used actually in a Lockheed satellite in the early 90s, but used a hydrazine propellant for both monopropellant and arc jet propulsion. Okay, so that's one example. Another example is using the newer green monopropellants or ionic liquids to do both monopropellant and electric spray propulsion. Okay, but notice that these have separate thrusters. Okay, so there's a higher inert mass penalty associated with doing that compared to if you were just to have a single thruster with the dual mode Hall thruster. So the ultimate system then would have a shared monopropellant, but also use the same thruster to do both chemical and electric modes. Okay. So just to describe some of the benefits of why you would want to have both chemical and electric propulsion on the same spacecraft is one, it has been shown that you can design maneuvers synergistically. So use chemical propulsion when needed and use electric propulsion when needed. And that can increase the deliverable payload. Okay, so simple example of that is if you were to use electric propulsion in Earth orbit, say to get to a Mars transit orbit, you'd find that electric propulsion system has a long spiral out orbit. Okay, and so it can be shown that it's better in a gravity field to get out of it as quickly as possible. But then in interplanetary space, you're not in a large gravity field, so you can use the electric propulsion system and then do your final injection into Mars with chemical propulsion. And it's been shown that that architecture is better than if you were to have solely chemical or electric propulsion. Okay. The other thing you can imagine is that can enable missions that cannot be accomplished by chemical or electric propulsion alone. And then really one of the main benefits to this that we've had success in selling to people or marketing to people is the flexibility this offers. Okay, so imagine if you've got a propellant that can do either chemical or electric propulsion, you can choose whether you want to burn that propellant in a chemical mode or accelerate it in a high specific impulse electric mode at any time during the mission. Okay, so that gives you the flexibility to change mission types on the fly, essentially. So if you've got, say, debris coming in and you were doing station keeping with the high specific impulse electric mode, you can then switch to chemical mode and get out of the way of that debris quickly, and then maybe use the electric mode to slowly go back to where you were originally. Okay, that's one example. There's many other examples where this has been shown to potentially be beneficial. One's constellation phasing. I already mentioned debris avoidance, deorbit as well. And then sort of this multi-mission platform concept. So if you have a single propulsion system where you can choose to do chemical or electric maneuvers on the fly, it means you can design many different mission types with just that single propulsion system. Okay, so if you have, say, one propulsion system that's off the shelf, ready to go, and that can do many different types of missions, it means you can meet the mission requirements for many different potential customers without having to design a new propulsion system every time. Okay. So sort of the commercial applications, DoD, I can tell you, is very interested in resiliency, so the ability to adapt on the fly, and also highly configurable constellations. So being able to change configurations as things on the ground develop is of interest. NASA is very interested in obviously lunar and interplanetary missions. Got one example shown here, and that's sort of like the example I mentioned earlier. But this, you've got a CubeSat that is essentially on the SLS if it ever launches, and that gets injected into a translunar orbit. Now, it's well known that it's very hard for CubeSats because they're so mass and volume limited It's very hard to inject into a stable lunar orbit. Okay, it's you can't do it with electric propulsion. It just does not provide enough thrust. But obviously, chemical propulsion takes a lot of propellant to do that. So you could have the option of just getting into a high lunar orbit, or with our multi-mode system, you could do the injection with a high thrust burn, and then have propellant left over and use that leftover propellant very efficiently to change orbits while you're around the moon to do reconnaissance or some imaging, or just use for station keeping, whatever you need. Okay, so the first sort of technical question that I looked at when I started looking at dual mode systems was, can we create a propellant that will work in both chemical and electric modes? Okay, and we looked at two specific systems. One was a monopropellant and one was an electrospray system. There were several reasons why that I won't really get into why we chose monopropellant and electrospray. But the answer is yes, there are propellants that will work in both chemical and electric modes. So that's sort of centered around these ionic liquids. So an ionic liquid is a liquid salt below 100 degrees C. So these are salts like table salt. You have sodium and chlorine. So sodium is the cation, chlorine is the anion. But table salt melts at around 600 degrees C. Okay, so ionic liquids are big, bulky organic compounds. So they have an ion. So this is an example of an ion. And they have an anion. But because they're big and bulky, they actually exist as liquids below 100 degrees C, and some of them at room temperature. Okay, and it should be noted that these energetic ionic liquids, so ionic liquids that have a fuel and oxidizer component built into them, have been investigated as replacements for hydrazine chemical propulsion. And the reason they were investigated as replacements for hydrazine is they have essentially no vapor pressure at room temperature and pressure. And so that's an advantage because hydrazine is a really nasty compound and has vapor pressure, and you cannot breathe it in as a human and expect to survive, basically. So the handling and operational requirements for hydrazine are pretty restrictive. Okay, so it's desirable not to have those restrictions, hence the investigation into ionic liquids. Now, ionic liquids also have this property that they're electrically conductive, and the anions and cations are essentially dissociated in the liquid phase, which means they're really easy to extract from the liquid and use for electric propulsion. And that's done for the process called electrospray, which I'll explain in a second. But to be noted that before I started this project, this wasn't really a new concept, but people had been trying to electrospray a chemical propulsion ionic liquid. So I sort of took the opposite approach and said, well, we have these ionic liquids that have proven electrospray capability. What would it take to actually burn those, essentially? So came up with really a set of propellants. Really, if you go read the paper, it's more like a recipe guide rather than a single propellant investigation. But anyway, essentially the answer was to mix two ionic liquids together, and they do mix well together. Most of them do, some of them don't. And the one that we've worked with primarily over the years, and I could talk about this since it was developed in academia, is a mixture of oxidizer hydroxylammonium nitrate and ionic liquid fuel 1-ethyl-3 methylenedizoleum methyl sulfate, shown there. So this is the ethyl sulfate here, and this is the HAN ionic liquid. Okay, and the synthesis process is relatively straightforward, or at least it was back then. It's since changed now, but anyway. Basically, you can buy HAN in a 24% solution in water. We dry it in vacuum and then essentially just drop the hand crystals. It comes out as a solid. It melts at 79 degrees C. So at room temperature, it's solid crystals, and we just drop those in the imidazole ionic liquid, and those actually dissolve and form what's called a binary mixture of ionic liquids, sometimes called a double salt ionic liquid. But this blend is now known as FAM 110A, Froberg Aerospace Modern Propellant 110A. And so that is the propellant we've been working with mostly over the years. So one of the first things we did was prove that, this could ignite readily. And here's one of the experiments we did, essentially just heating up this foil catalyst material at a certain rate and measure the temperature below this droplet in the center there, and eventually it ignites. Okay, leaves some residue, but that can be managed. But it ignites pretty well and readily, especially compared to other monopropellants. The other thing we needed to know was, would it electrospray? So here's sort of an electrospray setup where you have a single emitter, which is essentially just a really small hypodermic needle. And then you have an emitter, and you apply a potential difference or a voltage between the emitter and extractor, somewhere typically on the order of 3,000 volts. Okay, and you supply propellant or feed it in, usually by pressure, in this tube or needle. And then it comes out and forms what's known as a Taylor cone. So you see this liquid meniscus neck out here, and you can't see it because it's invisible, but it's essentially emitting ions from the tip of that needle, and they're accelerated through the hole in the extractor. Okay, so now that we have a propellant that works, let's go for the ultimate and do a thruster that can be used in both chemical and electric modes. So we came up with this concept whereby we use a catalytic microtube, so a really small tube that's on the order of that really small hypodermic needle I just showed you. And could we actually burn the propellant inside that needle? Turns out the answer is yes. I'm going to skip over a lot of that analysis because that could be a seminar in and of itself. But if you were to take that emitter and scale it with a bunch of emitters, say up to 10,000 of them, although you don't quite need that many, it could produce thrust on the order of normal CubeSat or comparative chemical and electric thrusters for CubeSats. But you can do it with a single thruster, thereby saving the mass of having to have two thrusters to do this. Okay, we've showed that, and there's some stats there, but we'll go through this fast. And so you can sort of see the effect of what multi-mode gives you. If you were to plot, say, the burn time it takes to do a maneuver and the delta V of that maneuver here on the y-axis, you see chemical propulsion is really good for producing delta V in a short amount of time, but it cannot produce anywhere near as much delta V as electric propulsion. And again, the downside to electric is that it takes a long time. Okay. With a multi-mode system, even though you can't do as well in a short amount of time as chemical, and you can't do as well in a long amount of time as electric, you can hit everything in between. Okay. And even certain missions that chemical and electric can't do, which is sort of this sliver right here. Okay, and so, what if you were to use separate thrusters? Well, the mass penalty for a CubeSat, and this is for a 6U CubeSat, I think, is really high. So carrying that an extra inert mass doesn't allow you to carry as much propellant, so you can't produce as much delta V. Okay, so in that case, you're better off just using the only chemical mission. Okay? Only chemical system. All right, so my company, our SBIR project, was essentially focused on designing and building that thruster and then demonstrating its operation. Okay, and we were able to do that. We demonstrated a manufacturing pathway to create the arrays of 100 to thousands of microchannels that you would need for this concept. And should be noted that's been done before. Microchannel heat exchangers are a thing, and we sort of took inspiration from that, but what we had to do is figure out how to put a catalyst material inside those channels. So that's what we did. And then we were able to demonstrate the operation in electric mode for array of hundreds of channels, and also in the chemical mode. And then the remaining question was, well, could you do it back to back, operated in chemical mode and then operate in electric mode? And we were able to do that. The other question we sort of answered, and I touched on this in my rocket propulsion class, if you were there, was doing the hazard classification of our propellant, which involved a bunch of explosive test demonstrations, and also determining its material compatibility. So that's sort of a high-level overview of the work we've done with Froberg Aerospace. A lot of it I can't get into details on. Just to show you some of it, here's sort of our microchannel array as it came after the end of the process. And you can see if we shined a light up to it, yeah, there's a bunch of channels there. All right, and so we made a test article that looked something like this. This is a heavyweight version, so this big old propellant manifold doesn't have to be that big, but since we're doing research and development, we wanted it to be that big for reasons. And you can see we were able to demonstrate this in chemical mode. Some of our first tests, you see a lot of smoke. We were able to figure out why that happened and reduce it in later tests. So here's actually right before our back-to-back demonstration. You can see the plume of this exhaust is basically transparent. It's only the interaction with the surrounding environment that you start seeing the smoke of the plume. Okay, so this is coming out pretty hot as measured by our thermocouples, but it's not visible to the eye. So it's fairly interesting. And we also were able to model what was going on in the thruster. So there's some pictures here, basically colorful fluid dynamic pictures here, and basically able to match our test results with those models, which gives us a good insight into how to improve the design of these and really understand what's going on in this mode. Our electric mode testing, you see our vacuum chamber here. It's not that big because, it's a small thruster, and the thrust doesn't have to be that large. You see our array here, a bunch of the emitter tips shown here, and yeah, it produces Taylor cones at the emitter tips. This is during startup, so they don't all start at the same time, but they eventually do attain electric spray. And some of our current is a function of time, so yeah, it produces a fairly stable current throughout its operation until you turn it off. Okay, so that's it for my presentation. Are there any questions?
Has a multi-mode propellant system been used in any missions so far, or is this still a developmental thing?
So we're still in development. We're working on, working toward two different missions. One is a lunar demonstration with a NASA program we're working with, and the other actually working with my alma mater, S&T, and their satellite team to do a just Earth orbit demonstration, and that's funded by AFRL.
Dr. Berg, for your electric, or for the multi-mode thruster, I think on that, forget which slide it was. Oh, sorry. If you if you go to slide 14, I think.
14, yeah.
So you say for the chemical mode, the monopropellant is fed into a heated catalyst tube. So
yes, yeah, you have to heat it to get it to ignite. Yeah. Otherwise, it wouldn't work, right? Because you wouldn't be able to electric spray it.
Okay, and like, like how much temp or how much heat are we talking about? Is it like,
That is classified.
okay, all right,
Actually, it's not classified, it's export controlled. But yeah. That's why I had to remove the axes on this.
okay, yeah. My other question was going to be, is that temperature on the axes?
Yep.
Okay.
I know you mentioned that compared to hybrid modes, like the dead mass is more favorable, but
Yep.
what sort of is that trade-off? Like how bad is it? The sort of added dry
Yeah,
mass?
so you can compute this. And so if you were to take a monopropellant system, and this is a commercial off-the-shelf advertised dry mass, and same with electrospray. And so those have totally separate thrusters and propellant tanks. And so essentially to get a hybrid system, you'd have to strap those together. So our system, while it's slightly more massive than either the separate monopropellant or electrospray system, it saves you, quite a bit of inert mass. Okay, and it's especially important for small satellites because you're already so restricted on mass. Anything you can save in inert mass is way more than adding another second of specific impulse.
I had a question about supercooling propellants.
Yeah.
And so this might be a mistake on my part, but I was always under the impression that like liquids have a constant density, like water is like the density of water doesn't really change. How cold do you have to get something for that to stop being true?
Not that cold. The density of water does change. If you go look it up, if you cool it below, the problem is with water is you don't have to cool it that much to get it to freeze. Okay, so that's why you don't really see a density change because it's going to freeze at 0 C versus room temperature at 20. But it does increase the density a little bit. And so the SpaceX propellants, and keep in mind the propellant mass is large, or the volume is fairly large to begin with. And so a little change in density will mean mass is increased quite a bit. Yeah, I don't know how much I can say. I'll just tell you the RP1 was cooled to about 20 degrees Fahrenheit. And they were planned to go colder than that, let's just say. So it does make a bit of difference. Even a little density change, because the volume is so large, means a lot of mass as well.
All right, well, I guess if anyone else has any other questions for AIAA or for Dr. Berg, feel free to stick around. But if not, I guess you can go ahead and close out our meeting here tonight. But we can all go ahead and thank Dr. Berg for coming out. So thank you.
Yeah, thank you for coming and listening.